So now we also want to talk about a few more properties. That is, we have already mentioned this, intrinsic carrier density. We said that when you have the semiconductor and it has a band gap, as we increase the temperature, there are these electrons and hole pairs produced, right? We have talked about it at length. Now, the question I'll ask is, how many electron hole pairs are produced? Okay. How many? Sorry, how many EHPs are produced? Well, I mean, we said that it's going to be temperature dependent. So let's take it to be at particular temperature. Right? So what happens? You just keep heating the material and then you're transferring more and more energy and you can break more and more bonds, right? That's what should happen. So how many? Can we break all of the bonds? Of course not. If you try to do that, essentially you're melting the lattice and lattice is gone, right? When you melt the lattice, that happens when bonds are all broken. But of course, we don't want to get into that extreme regime. We'll stay below that. So what happens at, let's say, a temperature of 300 or 500? Okay. So you're creating these electron hole pairs. That is the forward direction. Right? Now there is a sort of an equilibrium established. The reason is, if you think about it, in the forward direction, you have basically the bond breaking. Okay, this is one of the forces, which is actually you're supplying energy. So basically, bond is breaking, right? The other process, the counter process, is that you have lots of these electron hole pairs, in the lattice. They can recombine and form a bond again, right? So they can electron hole pairs can recombine. Basically, EHPs can recombine to form bonds, covalent bonds. So there are these two forces which are again going to act opposite to each other. When that happens, we have an equilibrium, right? So basically, equilibrium is established. I'm sorry, I just am spacing it in here. Okay. So equilibrium is established between these two forces. Okay. So I'll actually, derive a number for this later on. But for now, I want you to, accept that this number turns out to be at 300 degrees Kelvin for silicon. This number turns out to be 1.5 into 10 power 10. So I will need you to memorize this number. Okay. Sometimes, I use 1 into 10 power 10 when I'm discussing in the class for simple calculations. I'll say 1 into 10 power 10. So 10 power 10 electron hole pairs. But if you want to calculate precisely, it will be 1.5, excuse me, 1.5 into 10 power 10. All right. So we've already discussed how the thermal energy is actually converting into electron hole pairs, right? So now, if you think of germanium, what would happen? Germanium has lesser band gap. So band gap is given to be 0.66 eV here already. So what do you think will happen to the intrinsic carrier density in germanium at 300 degrees, of course? Okay. So please think about it. If you want, just pause the video for a moment and think. Okay. So because germanium has a smaller band gap, it should have a relatively higher carrier density. So for germanium, the number turns out to be 2.5 into 10 power 13 per centimeter cube. Okay. Then what about gallium arsenide? Gallium arsenide has a higher band gap. So by applying the same logic, gallium arsenide should have lower carrier density. And in fact, it turns out to have 2 into 10 power 6 as the intrinsic carrier density. So remember, whenever we are saying Ni, right? Ni is the intrinsic carrier density. We mean that Ni equal to N equal to P, basically. Electron and holes are produced. Electrons, we'll call them N. Holes we'll call as P. So when concentration of electron and holes is equal, and that is equal to Ni, we are saying, okay? This is intrinsic carrier density. We will repeatedly use this number throughout the analysis of silicon devices, okay? So, is it large? Is it small? What do you feel about the intrinsic carrier density? Okay, so if you think about it, it seems to be quite fairly large, right? 10 power 10. So 10 billion electron hole pairs. So it seems like a lot, but you should remember what is the atomic density. Okay, the atomic density for silicon was what? I mean, if you remember from I think lecture 2 or 3, I'm not very 2. I think it should be atomic density of silicon is approximately 5 into 10 power 22 per centimeter cube. So in a centimeter cube, you have 10 power 22 atoms, and out of which 10 power 10 of them are actually forming this sort of a electron hole pairs. So it is not actually a whole lot. Okay, you should remember that. Okay, and how does this number change? Intrinsic carrier density, how does it change with temperature? So we've already talked about it in our discussion initially. We said that okay, yeah, Ni basically is simply intrinsic. I'm just repeating it. Carrier density. Carrier density. Okay. So we said that intrinsic carrier density is going to be proportional to exponential minus Eg by kT. Okay. Well, I mean, the exact relation is going to be slightly different. Let's not. Yeah. In fact, it turns out to be 2 kT here. I should mention that. Okay. We will look at it one more time. Okay. Anyway, this proportionality I have removed, and I put a constant here for now. I will tell you later what this constant is. Okay, but how does that impact? Okay, we are talking about band gaps. We are talking about intrinsic carrier density. Is it real? I mean, we have to actually experimentally find out that, right? How do we experimentally find out these numbers? Okay. The way to do that would be to take a piece of silicon and then measure the conductivity or resistivity. Through that, you can estimate how much is the density of the carriers and how much is the band gap. One of the ways to do that is to actually take, let's for a moment take a logarithm of Ni, log Ni, and that will turn out to be log of this constant, whatever that is, minus Eg by 2 kT. Okay. So what I can do is, if you look at this, this is essentially an equation, right? This is an equation of a straight line. Okay. It's basically a straight line of a graph, right? Of a straight line. Sorry. Or rather, if you plot basically log Ni, right? With log of Ni, or Ni in terms of log scale if you plot in x-axis, in y-axis, and 1 over t on the x-axis. If you do this, essentially this equation will be satisfied. So essentially from the slope we can estimate how much is the band gap, and that is what is done here. In the picture on the right, we are essentially seeing temperature on the top, right? On the rightmost side you have lower temperature, and as you go to left, temperature is increasing. Or on the bottom we are showing 1 over t. I mean, it's 1000 by t, but anyway this is the proportionality, right? So this is 1 over t dependence. Okay, and y-axis is basically a logarithmic scale, log 6 to log 16, right? When you plot this, you see that various materials have these straight lines which are essentially indicative of the band gap. You see, germanium has a band gap of 0.66, so it has a smaller slope. But as you go to silicon, it has a band gap of 1.42 eV, so higher slope. And then gallium arsenide has even higher slope because it has band gap of 1.42 eV. And you look at the numbers. This is basically corresponding to, this is basically T equal to 300 degrees Kelvin. And you see that gallium arsenide has 2 into 10 power 6 carrier density, intrinsic carrier density, silicon 10 power 10, and germanium 10 power 13. So these are the numbers that you see, and which is consistent with what we were seeing. Okay. So whenever you plot this relation, so you can actually estimate basically Eg is estimated from slope of basically Ni versus log Ni, I should say. Okay, this is in log scale you should plot 1 over t, Ni versus 1 over t. This is in log scale. All right. So this is an experimental approach. You take a piece of silicon, measure the conductivity, or apply voltage, see how much current is flowing. From there calculate Ni, the carrier density, and then plot it with at 1 over T. So change the temperature of the sample multiple times, and then measure the conductivity, estimate the slope. From that you get the band gap. So this is one of the ways to actually estimate these material properties, band gap and carrier density and so on. All right, so good. Now, but if you think about it now, what is the resistivity or conductivity of silicon here? If you take silicon, this number, right, 10 power 10, it turns out to be the resistivity. If you calculate, resistivity turns out to be 100 kilo ohm centimeter. Then this is a typical number that we will actually tell you how to calculate this later on. When we will do that, we'll give you a formula to calculate this. But it's not equal; it should be approximate. Okay? Hundreds of kilo ohm centimeter. And if you think about it, the conductivity of the metal was 10 power, so the resistivity of the metal was 10 power minus 8. The resistivity of insulator was 10 power 12 or so, right? So there's a huge order of magnitude. Now this is also 10 power 5, so it's actually quite resistive. It's not really conductor, because a conductor would have 10 power minus 8 ohm centimeter, that sort of a resistivity, right? So it's quite high. What use is this? And also, if you think about it, we cannot really change the properties easily, right? Intrinsic carrier density, with temperature it changes, but it's not easy to change the temperature of your devices, right? If you want to operate the device at different temperatures each time, it's not going to be possible practically. And also, band gap cannot be easily changed. You pick a material, you work with silicon, that's not really a variable for you, right? So how do you change the conductivity or the resistivity of silicon? We showed that graph in the first lecture. We said conductivity of silicon can be from 10 power 5 to 10 power minus 3 or something like that we showed, right? And so basically, how do we achieve that?